So there will be a quiz on Wednesday, sections 4.1 through 4.3. So we kind of, start thinking about the exams that come. What?
We were going to have a quiz.
Or did you say you were here today?
No.
We'll see you outside.
I had faith he didn't have one.
Eric, can we sit outside,
If he did,
So you're definitely noticed that it's time for a quiz.
There's a stick.
All right. Questions from section 2. Are you ready? Yes. 6 and 7. Let's see if we can comment. Problem number 6. And what? How many ways can 10 men... All right, let's start. Problem 6. In how many ways can 10 men be seated on 10 the other seats so that person A sits ahead of person B and B ahead of person C? In how many of these seatings A, B, C sit next to each other? So I asked 2 questions. What about the first one? Can someone give me an idea how we can do that? Yes.
Fix A and then find out
True. We did something similar, so don't be afraid sometimes to break your problem into cases, because then, it might be much easier to calculate. So in problem 6, what can we do? We can put A on 1. So here's place. So so if you put A on a 1, then how many seatings are possible?
9.
Where B is ahead of C?
8.
Oh, lots of. What about the other guys?
we don't care.
We do. We do.
That'll make this section a lot easier.
So what? We had something similar last time. So this is just a little bulkier and C is in the game. So if you adjust the idea from last time, maybe we can solve the problem. So let's say A is on first. How many seats are there left? 9. That means 9 factorial. We're going to get a huge number. Altogether, there are 9 factorial different seatings with A on first. Do you agree? Among them, in how many of them B is ahead of C, and how many of them C is ahead of B? Should we have the way we talked last time about symmetry? So with A on first, it will be 9 factorial over 2. And then what? Just then let's see, and hopefully we'll make some conclusion to generalize. What if A is on second? No, but we also need to put someone here. So what would that be? What's it? Same thing. Probably we have a little less options for B and C. So B and C cannot be here. those two, do you agree? Among how many persons? 7. So that will be P72 on the left, and then on the right, what would that be? 7 factorial, do you agree? 1, 2, 3, 7 factorial, 4, 2. And then you continue and add them up, and that will be the answer. Not simple. But can we, so what is this? This is just breaking the problem into sub-problems that we discussed last time. And then we can do it the following way. Why would A sit in front of B and C? What are the other possible options? So for A, B, and C themselves, that A is ahead of B, C, or what? Of A and then C and then B. Or B, A, C, B, C, A, C in front of A, C, B, A. Now I'm not saying next to each other, but just when I compare 3 of them, these are 6 possible options. Do you agree? Yes.
Because only 1/6 of those possible options are interesting to us, can we just take 1/6 of all the combinations?
That's exactly what I wanted to suggest. Do you think that that's correct? Because for every configuration when A is ahead of B, ahead of C, I can make a communication where they exchange the seats, configuration where C, B, A, C, A, B, so all 6 of them should have the same number. Don't you agree? So the quick answer for that would be what? Take all the possible sequence, and then each of those configurations will show in 1/6 of those. Make sense?
So that's the quick way to do it?
What?
That's the quick way to do it?
Yes, although I'm always afraid of the quick ways.
Yeah.
You know, quick ways, sometimes you forget something, that,
Yeah.
you know, you think there is full symmetry and maybe there isn't
Yeah.
for something. So be careful with quick ways. But the good idea is maybe to think of quick ways, to practice this, and then to add up and to see that you get the same answer, and then you will believe more in the quick way. All right, so that was problem number 6. Problem number 7. In how many ways can you pick 8 cannons so that they do not attack each other? So what would that be? So what? If you choose one cannon on the place 1, 2, let's say, or let's say, yeah, 1, 4. Then what happens? Then you can choose the next one. When will 2 cannons attack one another?
In the same row.
If they have the same what?
Row.
Or column. So generally what? If I choose 1, 4 for the first one, then what are the only requirements? That I put what? Whoever's in the first row, on the first row, I choose something. I have to choose someone on the first row. Do you agree? And in how many ways can I do that? In 8 possible ways. Which one I choose on first doesn't matter. So generally, let me mention, let me do the short-term board. Whatever happens, and that's what we do very often in mathematics. Why does it have to be 8 by 8? Can I do cannons the same way 4 by 4? It's the same idea. So, if I choose 1, 4, and 2, 2, and then 3, 1, and then what? 4 who's left? 4, 43. Is this good, Chase? Yes. Why? Because each of, whenever you take 2 cannons, then they are on different rows and different columns, and then they don't attack one another. So what happens basically? If I list them, so that first row is in the beginning, second row is there, third row is there, fourth row is there, then my only question is, which column do I associate with each of them? Do you agree? So generally, all the configurations, so let me be configuration 1. Let me write configuration 2. Let's say 1, 2, 2, 4, 3, and then what, 4, 1. Is this the same configuration or different configuration? Different. Is it also valid configuration? So, how can I report this configuration? And if I keep reporting the configurations, what do all the configurations have the same and what do they have different? Look at the first component. They are always what? I listed 1, 2, 3, 4, 1, 2, 3, 4. Can I just erase this and just report the second component? Yes or no? So when I say 4, 2, 1, 3, that means in the first row take choose 4 column, then the second row second column, then first column, and third column. So generally what you see is here. What's that? What's it? One-to-one function. How do we call one-to-one functions in this section? We call them permutations. Because I just permute which numbers? 1, 2, 3, 4, and every permutation tells me which column to choose with that column, with that row, I'm sorry. By the way, this is very common in mathematics in different situations to report permutations, not only as strings, because when I write a string 1, 3, 4, 2, and that's how we see permutations. Is this number 1 first, yes or no? This one's second, this one's third, this one's fourth. So very often people report permutations as functions when the top row is always 1, 2, 3, 4, and the second row, because that tells you what the range is of your number and then what the value of the number is. So generally, I can always think whenever I see permutation, if you want, I would think of it as a function. In this setting, first number tells me the row, second one tells me the column. So in the first row, I call column 1. Second row, I chose column 3. Third row, I choose column 4. Fourth row, I choose column 2. So, one way or the other, number of possible correct settings for canons that do not attack one another is what? In this case, it would be number of permutations of 4 numbers, which in this case would be, but for P4. But in our case, for the full chessboard, it would be what? P8, which is in front of it. Exactly. So, and that is a common story in mathematics, where instead of counting what they ask you, you kind of assign one configuration. Yes.
How do we know what the properties of the cannon were their rooks?
Those are standard problems. That's, in every problem you can ask me what, whenever assume some context. So it's generally assume that you know the context, how cannons or rooks attack one another. Unless in a standard way chess.
When I'm thinking cannons, I'm thinking a gun that shoots directionally. Therefore, it can shoot in only one direction. So you could have
Okay,
four on the same row.
all right. So generally, I should have explained it better. Yes. So if it's chessboard, I assume cannons or rooks.
Yeah,
The other
I
thing.
understand.
And then now, I hope it makes more sense.
Yes.
Yes, sometimes questions will depend on the context, and we assume that you know the context, but maybe we should make it more precise. Like if it's a full hand, then what that means, as I said, not everybody needs to know card game. All right. Are there any other questions? Yes. Number 4, what happened there? How many ways can 5 men and 5 women be seated around the circular table, and a table if the men and women are supposed to occupy alternate seats? Again, don't try to call formula. Imagine making one such design and then see how you would accomplish that. There is one more thing here. Yes, 10 theater seats. That's good because I was worried. No, 4. positions labeled or not. So if the positions on the circular table are labeled as 1 through 10, then we will consider different positions if we rotate the table. So that always should be specified. So I will do, in the regular, I would say, since I didn't specify that the positions are labeled, we'll assume that it doesn't matter on which place everybody sits, but who has which neighbors, okay? On the left and on the right. So generally what? What we'll do is the following. Let's say that first couple, so let's say the men of the first couple will sit on any seat. And this table will be rotated until certain position on the table points toward that person, and that means that person can sit in only one possible way. Is that clear? That's how we usually fix the rotation. And then what? If that happens, so no counting, just one way for the first men to sit. Then what happens? I will skip one place for ladies, like this. So there are 5 positions on men. Is it completely determined where men have to sit now? Yes or no? Once we choose where the first man sits, then all the other are absolutely predetermined. So that means those 4 seats are reserved for men, and then these 4 men can seat wherever they want, and that would be 4 factorial. Okay. So I position the men. So what happens with women now? So here's men 1 from the first couple, second, third, fourth, and then what? Let me read carefully. If the men and the women are supposed to occupy alternate seats, did I say in the text that men should sit next? No, they're not even men and wives, so that's even out of question. I was reading.
Wait, wouldn't the first man have 5 choices?
Was it? No, because all those 5 choices are considered to be the same, because the rotation of the people around the table would make all these choices the same. But if you, as I said, if you do not consider 2 positions that differ just by rotation to be the same, then I would put 5. So those are 2 possibilities. So you have to read that text. What happens now? Now, actually, there are those 5 positions for women, and then what happens? 5 factorial as a choice for men, and that's it. So generally what happens here, I had a shuffle, 2 completely separate shuffles. So one shuffling among the men, one among the women, and then since seats were in a way reserved for one or the other group, then that is the number of choices. And generally what, if you wanted to say 5 factorial for men times 5 factorial for women, and then divide by 5 for the rotation, but why not by 10? Because rotation can go from men to men, and that's possible. that the marker points to that first woman, so to take care of the rotation. And then what happens? Then husband of that woman sits either left or right. Do you agree? So that's in two ways. So once you fix where the husband sits, let's say wife one, husband one, then first couple already chose a position, and then the second couple must sit in the next two seats. And then which couple, so again, there are 9 pairs of seats for 9 remaining couples.
So 9 factorial.
So that's 9 factorial. And then what happens? Now, a rotation between the couple. So if you want to get the final arrangements, you say to each couple, seat whichever way you decide. And then what happens? So this is just each rotation in one couple has no influence on the rotation of the other couple. They are components of this final arrangement. So, for example, second couple, this first one is kind of working out. Second couple has 2 options, okay? Men left, women right, or the other way around. Third couple also has 2 options. So then each of them could be a little combined with each of them. That's why, because it could be order is important, but order of choosing. Symbol for permutation, for combination, I mean number of combination will be CNR. And later on you will see next week, we'll study combinations with repetition, then we'll just put the bar above it, and that will tell us that the repetitions are allowed. So on the screen you can see one attempt to explain the form. Oh yes, it's also important to not mention that. There's a famous choose symbol. So choose symbol, please don't write fraction line here. So it's N, choose R, and that's how we read it. And this one labels number of ways we can make or choose R elements out of N elements. You can also say the following. So you say, look at the following from the screen. Suppose I have the set A, B, C, D. So that tells me that initial material. In the initial material, I have 4 letters, so N equals 4. And I decided to choose 3 of them, so R equals 3. So what we are asking is how much is C for 3, which is the same as 4 choose 3. And then what we have on the screen is actually an attempt to get an idea how is the formula coming out. We'll write the formula in a moment, but let's try to derive it ourselves. What did I write here on the screen? Every permutation of these 4 elements, I'm choosing strings of 3, do you agree? And how many is that? So we know from before, we know that P for 3 is 4 times 3 times 2, which is 24. Do you agree that that's what we learned last time? But what happens here? I underlined here 6 strings. ABC, ACB, BAC, BCA, CAB, and CBA. Are all 6 of them in the list, yes or no? Why? Because each of them has a different order as strings. They are different because what? Here, second letter is B, second letter is C, so they are not the same strings. And again, whenever you compare an array 2, they are never equal as strings. But what happens? Do they contain the same material? What is it? They are all made out of ABC. And this time we won't count them as 6 different objects, we'll count them as a 1 object. Is that clear? So the only thing that matters is material. So all these ABC, let me write ACB, BAC, BCA, CAB, and CBA, they will all be counted as 1. And actually 1 what? 1 subset. And who are the elements of the subset? That's why now I'm going to do curly brackets to say I just care who's inside and I don't care how they are listed. So who are the elements? So what happened? In the count for a permutation, they count as 6. As combinations, they count as 1. So what should I do? Total count. So to get C for 3, in this case, I should do P for 3, and I should divide it by what? 6. Or that's what? P4. Why 6? Because those are all the possible ways to shuffle ABC, which are factorial, which is over 3 factorial. Do you agree with this? And this is what we always do. So formula, let's make a formula again. CNR will be PNR divided by what? Exactly. Then if we recall what the formula for PNR was, what was that formula? If you remember last time, it was n factorial divided by n minus alpha. That was what we had from before, now also times alpha. This is the famous formula for combination. It's n factorial over n minus r factorial r. This is what we call closed formula. This formula is good when you make proofs or something like that. But for practical purposes, we don't use that formula. We just do something much quicker because there's tons of cancellations. So for example, C72. How much is C72? Actually the same way as I told you, like instead of writing all this and canceling tons of factorials, here's how I calculate it quickly. I start with 7, and then I go down, as last time, keeping in mind that number of factors should be 2. So it's just 7 times what? 6. And on the bottom, 2 times 1. That's 2 factorial. That's it. So how much is this? 42. But how much is C75? Actually, before I do that, I want you immediately to notice one very nice property of combinations, and that is, if these two numbers are complementary to 7, then a number of combinations is the same. So, what is it? Property. We'll talk more about properties of combinations. And that is, n choose r is the same as n choose n minus r. That's why I call them complementary. They add up to n, and then you can choose whichever one you like more. Why is that true? Is it easy to prove this here? I remember once I asked this question on the exam, and I don't think there are 2 good responses. And you know what is the proof? Just this. Look at this. If I put r, so is this condition symmetric for r and n minus r? Yes or no? So, when you write the proof. How much is n minus r? By definition, it's what?
N minus
N factorial over, now what it says is n, rule says, whatever this number, subtract them, so subtract them, n minus r factorial times n minus r. So I used that rule where r was replaced by n minus r. But what happens that to b? How much is n minus r?
R.
R. Did I get the same thing, yes or no? Which is n choose r. So that's why, if I want to calculate 7 choose 5, I'm not going to do 7 choose 5. I would rather do which one? 7 choose 2, which is shorter r. And then again, as we go, I will use 5. Do we understand the configuration? Once again, it's important that elements do not repeat. We fix how many of them are chosen, and order is not important. That means we are just talking about subsets and not strings. So permutations are associated with the word strings, and combinations with the word subsets. And what happens now, we'll just go from problem to problem and see how we recognize which one is which. Formula, okay, there's problem 432. type 11 first, and then you go math, and you go oops, probability, and then it will tell you here is NCR symbol. So generally 11 is 11, then you say I want combinations, and then we put type R. How much is R in our story? 4. 4, so it is 330, and then the calculation. And then you can see there also there is NPR, and V factorial. Problem number 2. I mean, second part of this story. They say suppose that two persons insist on working together on the team. In how many ways can we make the team? Let's make sure that we understand this condition that they insist on being together on the team. How would you understand that? Insist. Was it? No, oh no, because then you would have more players than the other team, no. But when you insist on being together, that means what? Meaning what? Either you choose us both or not. So if one of them plays, the other has to play. If you don't want me, then you cannot have the other guy as well. Is that clear? So this means, let me call them A and B, play together. That means both or none. Do you agree? Do you see the key word? Or. So what is that telling you? And. Because these are not components of the team. You have two ways to design your team. With both of them or without them, and there's no overlap. Is that clear? Because this team cannot have and not have them at the same time. All right. If I want the both of them, then what happens? And they already took 2 spots, so there's no choice here. They took 2 spots, and you have how many openings now? How many was it? 4. Sorry. 4. So if they chose 2 spots, then how many spots are available? 2 out of how many? 9, exactly. 9 remaining candidates, and then you choose 2. Then let's design those when they are not on the team. That means what happens? How many spaces are open? Not 11, because they still now they don't want to be considered. So that means those 4 must be chosen out of other 9. Exactly. That's it. Do we understand this design? So here it is. First we broke into 2 cases, and then for each of them we did a separate count. So if they are both on the team, that means there's no choice there. That's already prefixed. And then we have just 2 spots for 9 candidates. But if they are not included, then we have all 4 spots for the remaining 9 candidates. Again, so there's no choice with them. Is that clear? It was always out of 9. Then for just 2 or for just 2. What about third version? I don't know if it will come later on in the notes, but let's make it. What if 2 persons you don't want to put on the team together? If they insist not to play together, they're really on bad terms. Take it. Minus for what? Minus for what? You might be right. You might be right. But you might be careful that subset, because minus means that your set is subset of and the one that we calculate is a subset of, but which total? Be careful about that. I agree it could be done that way. But I would rather break it into stories. So what does it mean? Yes.
So we do one with one of the team, one of the players not playing, like 10 choose 4, and then another 10 choose 4.
No.
Because you said they're both of them not playing at the same time, right?
No, they said, we don't want to play together. Actually, why did I say no to Eric? I don't know. She was absolutely right. No, she was just fine. They're nothing special, because what? They are, so, are we choosing?
Choosing three total.
3 total.
So 5 choose 2 and 4 choose 1.
3 total. Out of how many? 9. But this is not really how we make the choice, because if I say 9 choose 3, what would that be? Yes, I don't even pay attention who is who there. Really, I have 9 persons that choose 3, that's it. But if you want a special design, then you cannot use this. So really, sorry about this. So what happens? Well, I have strictly prescribed number of men, a strictly prescribed number of women. Really?
Is it 5 choose 2 times 4 choose 1?
Do you agree with his decision?
Yep.
Well, what happened here? He actually broke his election into 2 separate elections, like they're happening in 2 rooms. They are independent. So generally what? You have 5 men, and you must choose 2. Do you agree? Because that's how many men positions are in the committee. So you choose any 2 men out of 5. And also in the other room, independently from them, you choose any 1 woman out of these 4. Agree? And then what happens? Can I combine any choice from 1 room with any choice from the other? So that would be fine. If I either said 2 men or 1 woman, I would add it up. But here, I'm assembling the total list out of those 2 sub-lists, and that's why it's fine. Is everybody okay with this? Good. Now we'll just do variation of this problem to see how do we react to other restrictions. It says how many teams have at least 1 woman. So what does it mean at least? Can I break at least into a few situations of this type? Yes or no? At least 1 means what? At least 1 woman. That means what? Exactly 1 woman and 2 men. Or now we have alternatives. And then you see we sign there. Would there be a plus?
Yes.
Or what? 2 women, 1 man. Or all 3 women and 0.
This one, can you do this one faster?
For the complement?
You are becoming specialized in confidence. That's good. But let's connect with this guy, and definitely there will be another solution. 1 woman, 2 men. Is that exactly the same problem as minutes ago? Yes or no? So that is what? 4, 1, 5, 2. Then I do plus, because I'm not assembling those. Those are alternatives. Or I can do what? 4, 2, 5, 1. I can do something that I didn't tell you. How much is 5, 0? How much is 5 choose 0?
It's just 5.
I'll come back. It's 1, and I'll tell you. So let me finish this story, and then we'll talk about those exotic cases in a moment. So what would that be? 4 choose 1 is what? 4. And 5 choose 2 is 10. So 4 times 10 is 40. Plus 4 choose 2 is 6 times 5 is 30. 4 times 3 is just 4. And this is 75. Split it. But faster solution. What can we do? Is now counting all these categories, we can say the following: go for the complement. Is that what you suggest there?
Yeah.
So what is up? So they're all together. How many committees altogether?
You do teams for how many?
So 9 choose 3. Total number of committees. Now let's remove those that have no women.
5, 3.
Why 5, 3?
Yeah, 5 men.
You are choosing all 3 among the men. So minus no women. Which sometimes going to opposite events makes things easier. All right, a couple of exotic calculations that I used here. So values that involve zero, first, 0 factorial. How much is 0 factorial? Can you comment that? We already did that, very good. So now, how much is n choose 0? If we do go calculationally, it says n factorial over, then you subtract, then n minus 0 factorial times 0 factorial. N factorial and n factorial are cancelled, 1 over 1, which is what? 1. What is the modeling reason? If I have 10 persons and I want to choose nobody, in how many ways I can do it? In one way, just choose nobody. And easily. So modeling also supports that calculation, even if it sounds wrong. This is very nice problem. This is, yes.
So I already know this is wrong, but I was wondering why. Let's say we have the exact same problem, we have 3 spaces, there's almost 9 people. We want to know how many of them are filled with at least one woman. Why can't we just choose our woman and say there are now 2 spaces?
What's that, three
Three spaces.
spaces, is order important or not? The same way as here, just call me.
Same way.
Same way, okay,
So we have, so let's just say we've already decided that there is one woman in there. Because that's our minimum requirement.
Yeah, okay.
So then we have 2 spaces left to fill with 8 people. And we don't care if there's more women or there's no more women because we already have at least one woman. So that should be 8 choose 2, so we don't get 7 people.
Interesting question. Let's analyze. So what happened? The way Jonathan suggested is this. So you choose one woman to say, we are sending one woman and that's it. So then, in how many ways can you do that? Choose that first one in 3 different ways. And then, the rest can go either way, do you agree? Now I have how many spots? 2 spots. How many candidates? 8. Which is 3 times 8 times 7 over 2, which is 3 times 38, which is 84. Huh. What went wrong? I got too much. What's wrong? And this is very good example, but I heard you, I liked it that you asked this. Because shows you how easily one can make error if we are a little careless. You know, what happens here is we're not writing all those possible choices. We are kind of imagining some analogy and so on and so on. Yes?
Is it combining the idea that you could choose the same woman twice?
No, you cannot, because whoever you chose here, that's why you reduce the number of candidates. That's good. But here is why we got the extra count. Let's say women are A, B, and C, okay? So then what? When you say 3, you say I can choose A. And then I can choose B and 1 man. Okay? And that's counted on A count. On A is 28. So with A on first, there are 28 options. With N is BM option, really. Then if B is chosen on first, can I choose AM out of 28, really? Is that the same one? You count it twice. That means those are not disjoint together. What you did is actually, you combine the idea of order matters. Who was chosen first, here actually does matter in a way. So these are not pure combinations. So see how easy it is kind of to do extra count or to meet someone if you are not careful with design. I'm very glad that you asked this, because that's what we repetition allowed.
Yes.
What is this?
Not this.
Not this, exactly. So this looks strange. This looks like first order is important. This looks like permutation. Don't you agree? And repetitions allowed. We didn't study that. So what happens? Yeah.
Instead of having the permutation where we get less and less possibilities, we're just looking at every one of them individually. So we have 2, which is a possibility, 10 to 10, and how many of those will we get?
I like what Jonathan says. So he said the following. He just did multiplication principle. So he said, how many options do I have on the first? And that's what it is. Permutations with repetitions allowed. We have 2 options here, either 0 or 1, right? Then 2 options here, 2 options here. So altogether there are 2 to the 10, 0, 1 strings.
It's just like the whole story.
And that, by the way, that's what 1 kilobyte. To the 10th, exactly, we have 10. All right, so, my question is now, this column reports all the strings, but they don't want all the strings. What do they want? Those that have how many ones? Exactly 3 ones. So that's a problem. Not all of those are good. I only want good ones, and that means those that have 3 ones and 7 zeros. Do you agree? So what's my freedom here? But when it's so much prescribed, what's my only thing that I need to decide? Okay, so what do I need to do? To locate what? Both of them or just one type of them? If I decide where to put my ones, then zeros on all the remaining spots, do you agree? So what do I need to do?
Is it 10 times 9 times 8?
Almost, but order, is the order important? And here is a tricky word where we said here order important. Which order? Of course, there are many orders in the problem. Not order how they are written, but I'm choosing 3 houses for my ones. And if I choose this, and then I choose this, and then I choose this, does it matter? Or if I choose this and then this and then this, is that the same thing? So what am I doing here? I have 10 houses, agree? I need to choose 3. In which order do I choose them doesn't matter as long as I know which 3 I'm choosing. So what is this actually? Oh, how many elements? 10. How many do I choose? That's it. So actually what happened? So I'm crossing all of this because it's confusing. And actually what happens? I need to choose 3 places to host my ones. Agree? Nothing else. Once I choose where to put ones, all the others will go zeros. Is the order of choosing, not order of writing, is order in which I choose those 3 important or not? If I choose 3rd one first, and then 9th one, and then 6th one, or 5th one, whichever one it is, or I choose 6th one first, and then it doesn't matter. The order of choosing doesn't matter. Order in which I choose them does not matter. Does this sound like what we are studying today? So that's what? Then choose 3. So you see, strings are completely opposite from this. They have repetition, the order is important, but choice of location for ones is not. So that's what I wanted to count, and of course each choice of locations gives me ones. So that's why I created a question for the one that I was able to solve. And that's something that you have to be careful about. You cannot just learn the buzzwords and then just automatically call the point. Particularly, don't try, to solve problems problem by just calling for it once. Usually, that's all. I don't think that I would ever ask a problem or just, oh yeah, that's verification. Here's, I learned it last